In this video, we're going to talk about how we construct or approximate atomic wave functions. So let's first talk about variational theory. So when we think about applying variational theory to larger systems like atoms and even molecules, we're going to think about often defining our trial wave function if, say, we have three particles that are at spatial positions R1, R2, and R3. We might define these as the product of three known wave functions or model wave functions at each of the positions R1, R2, and R3. And so also, if we're going to think about atoms, we need to talk about our fourth quantum number. So maybe you recall, once upon a time in general chemistry, that there was a fourth quantum number for the atom. And so if we look at sodium's atomic line spectra or emission spectrum, we actually see that there are two lines very closely spaced together in the yellow region, but we get this doublet. And in fact, this is not the only place we see a doublet, but sodium's is very prominent and very bright. So it was able to be seen even with lower resolution spectrometers. And so this clued scientists in the early 1900s that there was a component missing. And this component that we were missing in our wave function leads to the fourth quantum number, which we denote m sub s. And so this is the spin quantum number, and we have eigenfunctions to account for our spin of an electron, and we call these eigenfunctions alpha and beta. Now, we're not going to go into mathematically what alpha and beta look like, but spin has the operator of s hat squared, and if you apply s hat squared to alpha, you get an eigenvalue of positive 1/2 times h bar. And if you apply the spin operator to beta, you get an eigenvalue of negative 1/2 h bar. Well, as you might recall, positive and negative 1/2 are actually the available possibilities for the value of m sub s. We call positive 1/2 spin up and negative 1/2 spin down. Note that alpha and beta are orthonormal wave functions, just like all of our other quantum wave functions. And so now we can think about defining, we'll use a capital psi to distinguish that this has a fourth variable. Here, that fourth variable isn't time, it's another component. So if we have our wave function psi for some atom or particle, we can think about it having the spatial dimensions r, theta, and phi, as well as the spin dimension, which we'll call sigma. And we can write this as a spatial wave function, like one of our known hydrogen atom wave functions, times either alpha or beta as a function of sigma to denote the spin of that electron. So you may also recall the Pauli exclusion principle, which we told you in general chemistry meant that each electron needed 4 unique quantum numbers. But actually, the Pauli exclusion principle is a little more complicated than that. It states that atomic wave functions must be antisymmetric with respect to the exchange of 2 electrons. This means that if you take an electron that you've previously called 1 and an electron that you previously called 2, and you swap their notations such that number 2 becomes number 1 and number 1 becomes number 2, you'll make your wave function negative. So if we had some psi of electron 1 and 2, and we exchanged electrons 2 and 1 and called them opposite of what they were originally called, our wave function would be negated. This is kind of a strange thing. And so we have a methodology of multiplying our hydrogen atom-like wave functions in order to get wave functions which will be antisymmetric, which will follow Pauli's exclusion principle. And this methodology is called the Slater determinant. And so you may or may not have heard the word determinant before in a math class. If not, we're going to briefly discuss a 2x2 determinant. You don't need to know how to do determinants to get through this class, but I do want you to be familiar with at least a 2x2. So say we have some wave function, again, capital psi, because we're going to include spin, and maybe this is for a helium atom. So it has 2 electrons, electron 1 and electron 2. we're going to set up what's called a determinant, which is going to look a little bit like a matrix. And in the columns, column 1 is going to include the first possibility for a wave function. Column 2 is going to include the second possibility for a wave function. We'll define those possibilities here in a second. Row 1 is going to only consider electron number 1, and row 2 is only going to consider the electron that we call number 2. So one possibility for an electron in a helium atom would be psi1s, and this is R1 because it's the position of electron 1. And so we're saying that electron 1 is in a 1,0,0 or 1s hydrogen-like wave function spatially, and we'll say it's spin up, so it's multiplied by this alpha function. Well, we could just as easily, instead of putting electron number 1 there, put electron number 2. And so remember, the second row represents electron 2, but it's still this first possibility of a 1s orbital that is spin up. Another possibility for our electron is to be in the 1s orbital spatially, but be spin down. So multiplying instead of by alpha, we're multiplying by beta, that function that represents spin down. But just like we could put electron 1 or electron 2 spin up, we could also put either electron spin down. So we'll put that other combination down here. And so now we need to know, how do we solve a determinant? So very briefly, if we're going to solve a 2 by 2 determinant in math, say we have this determinant where we've got a, b, c, d, first we would multiply across the diagonal from a to d. So we're going to have a times d, whatever that might be, and then we'll subtract the cross diagonal product, which would be b times c. Let's try this with our helium atom matrix. This would give us psi1s R1 alpha 1 times psi1s R2 beta 2. So electron 1 is spin up, electron 2 is spin down, both in the 1s orbital, minus psi1s R1 beta 1 times psi1s R2 alpha 2. So this would be electron 1 spin down, electron 2 spin up, both in the 1s orbital. So we have a linear combination of two possibilities, both of which are products of two complete wave functions, including that spin function. And now we could prove, if we wanted to, if we exchanged in our determinant electron 2 and electron 1, and we resolved for psi2,1, we would see that psi2,1 is equal to negative psi1,2, which obeys the Pauli exclusion principle.